All right, welcome. Today we're going to dive into a really cool corner of calculus that looks super familiar at first, but it's got a crucial twist. We're talking about the derivatives of hyperbolic functions. So you probably feel like you've got your derivatives down by now, right? You've spent hours memorizing the rules for all sorts of functions. But what happens when you run into functions that look like the ones you know, but they act just a little bit differently? You know, to really get a handle on these hyperbolic derivatives, the best place to start is actually somewhere we're all comfortable, with their famous cousins, the standard trig functions. Let's do a super quick refresh. Okay, check out these two fundamental rules. We all know them. The derivative of sine x is cosine x. Simple enough, but notice, the derivative of cosine x is negative sine x. That little negative sign, that is the key to this entire thing. Just lock that away for a second.
All right, now for the main event, the hyperbolic functions. And at first glance, they look like a perfect mirror of what we just saw. But like I said, there's one crucial, kind of mind-bending twist coming up. First up, we've got the hyperbolic sine, which we pronounce sin of x. Its derivative is the hyperbolic cosine, or cosh of x. Okay, so far so good. No surprises here, right? This perfectly mirrors sine becoming cosine.
But here's the twist. The derivative of cosh x is just sinh x. Take a really close look at that. Something's missing, isn't it? Exactly. This is that moment in class where everybody kind of stops and double-checks their notes. You're probably thinking the exact same thing right now. Where in the world did that negative sign go? And that's the big reveal. It's positive. The single most important thing to remember here, and the most common place people slip up, is that the derivative of cosh x is positive sinh x. It's not negative. And the reason for this actually comes from their definitions using Euler's number. Cosh of x is based on e to the x plus e to the negative x, and when you differentiate that, the signs just work out perfectly to give you a positive sinh x. Okay, so we've got this new kind of weird rule. But here's the great news. Even though the function is different, all the derivative rules you've already mastered, like the product rule, work in exactly the same way. So let's put it to the test.
We're going to find the derivative of y equals x times sinh of x. You can see right away this is a classic setup for the product rule. We've got one function, x, multiplied by another function, sinh of x.
Let's just walk through the steps together. First, we identify our parts. We'll say f is x, so its derivative, f prime, is just 1, and g is sinh of x, and its derivative, g prime, using our new rule, is cosh of x. Step 2, we just state the product rule, f prime g plus f g prime. Finally, step 3, we substitute everything in and simplify. And there it is. The derivative is sinh x plus x cosh x. See, the process itself is exactly what you're used to.
All right, now that we've nailed the product rule, let's keep that confidence going and tackle another familiar process, the quotient rule. The setup looks a little more complex, but I promise you, the core idea is exactly the same.
Okay, so here's our function. Y equals the hyperbolic tangent of x divided by 1 plus x.
So let's break this down using that low d high minus high d low mnemonic. The high part on top is tan x, and its derivative is sec squared x. That's hyperbolic secant squared. The low on the bottom is 1 plus x, and its derivative is just 1. Easy enough. Now we just apply the rule, plug all those pieces into the formula, and we get our final answer. See? It's just a matter of plugging the right pieces into a rule you already know.
So at this point, you're probably thinking, okay, I get the mechanics, but why? Like, when am I ever actually going to use this stuff? And that is a totally fair question. The answer is actually all around you. I mean, what is the real-world application for these seemingly abstract functions? It turns out they describe a shape you see literally every single day.
And here it is. Every single time you look at a telephone wire sagging between two poles, or even a chain hanging from 2 points, the curve that it makes isn't a parabola. It's a special shape called a catenary, and that exact shape is described perfectly by the hyperbolic cosine function. That is its real-world power. Pretty cool, huh?
So we'll end on this thought. We've seen how trigonometric and hyperbolic functions are almost perfect twins, but they're separated by this one tiny, crucial negative sign. This pattern shows up all over math and science. So as you continue your studies, just keep an eye out for it. What other concepts look almost identical, but are hiding one game-changing difference?